And we'll see the Shanghai factory continue to scale quite a bit from where it is right now. I think we really could expect that to be, over time, a factory that produces over 1 million vehicles a year. We also introduced the lowest cost solar in the US. It's only $1.49 a watt. We also got 4 consecutive quarters of GAAP profitability, where the value of Tesla is going to be like total, just on the vehicle side, total vehicles produced times the value of autonomy. We also have consistent free cash flow generation. Just tightening up and having the parts move very quickly to the factory, put it in a car, get it to a customer, makes a massive difference to cash flow generation. And I mean, that's why it's extremely important to have a factory in each continent. 3 new factories, incremental, on, well, we have one already, on 3 different continents. Shanghai, we're expanding to Shanghai with the second phase. Berlin is making rapid progress, and Texas is making even faster progress. Like the Model Y made in Berlin might look the same, but it actually is made in a much more efficient way. Fundamental good of Tesla, it's like if you look back in history and say, what good did Tesla do? The good will be to what, by how many years did we accelerate sustainable energy? That's like the true metric of success. Tesla's contribution, we've delivered over 1 million electric vehicles, 26 billion electric miles driven, and many gigawatt hours of stationary batteries, 17 terawatt hours of solar generated. The 3 parts of a sustainable energy future are sustainable energy generation, storage, and electric vehicles. So we intend to play a significant role in all 3. Goal number 1 is a terawatt-hour scale battery production. Tera is the new Giga.
We're talking about 100x growth in batteries for electric vehicles to achieve this mission.
You basically need on the order of roughly 10 terawatt-hours a year of battery production to transition the global fleet of vehicles to electric.
And the average vehicle lasts 15 years, so we're talking about 150 terawatt-hours, give or take, to transition the whole all vehicles of all types to electric. And then on the grid side, 1,600 times growth from today's grid batteries to go 100% renewable on the grid, and to take all of the existing heating fossil fuel uses in homes and businesses 100% electric.
Roughly 20 to 25 terawatt hours per year, sustained for 15 to 25 years to transition the world to renewable. Giga Nevada, 150 gigawatt hours per year is like what we probably expect to make out of there. But this is really pretty small in the grand scheme of things. That's only 0.15 terawatt hours.
We would need 135 fully built out Nevada gigafactories to achieve 20 terawatt hours a year. It's not scalable enough of a solution. We need a dramatic rethink of the cell manufacturing system to scale as fast as we can and should.
Goal 2, obviously, we need to make more affordable cars. I think one of the things that troubles me the most is that we don't yet have a truly affordable car, and that is something that we will make in the future. But in order to do that, we've got to get the cost of batteries down. The cost per kilowatt hour of batteries is not improving fast enough.
Early growth was promising, but you can see we're kind of plateauing. So that's what's motivating us to rethink how cells are produced and designed. To make the best cars in the world, we design vehicles and factories from the ground up. And now we do this for batteries as well. We have a plan to halve the cost per kilowatt hour. And it's not a plan that rests on a single innovation, some research project that'll never see the light of day. It's a plan that has taken creative engineering and industrialization across every facet of what makes a cell into a battery pack, from raw material to the finished thing. So as you can see, we kind of swept the key figures of merit, how much we can reduce the cost and how much vehicle range increases as we change the outer diameter of the cell. We found a sweet spot somewhere around 46 millimeters. But it's not just about a bigger form factor. Like, anybody could make a bigger form factor.
Any fool could make a bigger form factor.
We came up with this tabless architecture that maybe you've heard about, that basically removes the thermal problem from the equation and allows us to go to the absolute lowest cost form factor and the simplest manufacturing process. And this is what we mean when we talk about tabless.
So even though the cell is bigger, it actually has more power. The power to weight ratio is actually better than the smallest cell with tabs.
So when we put it all together and go to our new 80 millimeter length, 4680, we call this new cell design, we get 5 times the energy with 6 times the power and enable 16% range increase, just form factor alone. This is not just a concept or a rendering. We're starting to ramp up manufacturing of these cells at our pilot 10 gigawatt hour production facility just around the corner.
Yeah.
So just the cell form factor change enables a 14% dollar per kilowatt hour reduction, just that cell form factor change. And one of the most important processes is where it all begins, the wet process of the electrode coating. Wouldn't it be great if we could skip that solvent step and just go straight to dry mix to coat? And that's what the dry process really is about. You can see it here on a bench top. Literally, powder into film. As simple as that. But if you do scale it up,
Yeah.
what you saw before becomes this.
Yeah.
So you can see the motivation. A 10 times reduction in footprint, a 10 times reduction in energy, and a massive reduction in investment. Let's talk a little bit about assembly, which is next. The key to a high-performing assembly line is accomplishing processes while in motion, continuous motion, and thinking of the line as a highway, max velocity down the highway, no start and stop, no city driving. We're able to get to the point where we can implement assembly lines, one line, 20 gigawatt hours, 7 times increase in output per line. And the vertical integration with the machine design teams at Groman and Highbar and others allows us to really accomplish that, because we don't have all these edge conditions between one piece of equipment and another. We can design the entire machine to be one machine.
Eventually, every car company will have long-range electric cars. Eventually, every company will have autonomy. I think, but not every company will be great at manufacturing. Tesla will be absolutely head and shoulders above anyone else in manufacturing. That is our goal.
Okay, now let's talk about formation. 86% reduction in formation investment, 75% reduction in footprint.
What this translates to, based on what we know today, is about a 75% reduction in the investment per kilowatt hour. In a smaller form factor than Giga Nevada, that we could actually get to terawatt hour scale in less space than what we currently envision for doing 150 gigawatt hours. We will continue to use our cell suppliers, Panasonic and LG and CATL, and then long term, we're expecting to make on the order of 3,000 gigawatt hours or 3 terawatt hours per year. I think we've got a good chance of achieving this actually before 2030, but I'm highly confident that we could do it by 2030.
It's also an additional 18% reduction in dollar per kilowatt hour at the battery pack level.
But wait, there's more.
But wait, there's more. Let's talk about the anode first. Let's talk about silicon. Why is silicon awesome? It's awesome because it's the most abundant element in the Earth's crust after oxygen, which means it's everywhere. It's sand. And it happens to store 9 times more lithium than graphite, which is the typical anode material in lithium-ion batteries today. With this silicon, and the anode costs $1.20 a kilowatt hour. By leveraging this silicon to its potential, we can increase the range of our vehicles by an additional 20%, just this improvement.
Yeah, it gets cheaper and longer range.
And when we take that anode cost reduction, we're looking at another 5% dollar per kilowatt hour reduction at the battery pack level. And there's more. Let's talk about cathodes. What is a battery cathode? Cathodes are like bookshelves, where the metal, the nickel, the cobalt, the manganese, or aluminum is like the shelf, and the lithium is the book. And really, what sets apart these different metals is how many books of lithium they can fit on the shelves and how sturdy the shelves are. And you can see nickel is the cheapest and the highest energy density, and that's why increasing nickel is a goal of ours and really everybody's. And one of the reasons why cobalt is even used at all is because it is a very stable bookshelf. And the challenge with going to pure nickel is stabilizing that bookshelf with only nickel. And that's what we've been working on with our high nickel cathode development, which has 0 cobalt in it. Leveraging novel coatings and dopants, we can get a 15% reduction in cathode dollar per kilowatt hour. Beyond the metals, because a lot of people spend time talking about the metals, actually the cathode process itself is a big target. 35% of the cathode dollar per kilowatt hour is just in transferring it into its final form. And so we see that as a big target, and we decided to take that on. As you can see, a whole lot less is going on here. We get rid of the intermediate, metal, water, final product cathode, recirculate the water, no wastewater at all. And when you summarize all of that, it's to 66% reduction in CapEx investment, a 76% reduction in process cost, and zero wastewater. Much more scalable solution.
Yeah. To be clear, cathode production would be part of the Tesla cell production plant. So it would just be, basically, raw materials coming from the mine, and from raw materials in the mine, out comes a battery.
And on that note, the way the lithium ends up in the cell is through the cathode, so then we should obviously on-site lithium conversion as well, which is what we will do using a new process that we're going to pioneer. That's a sulfate-free process again, skip the intermediate. 33% reduction in lithium cost, 100% electric facility co-located with the cathode plant.
In fact, there's enough lithium in the United States to convert the entire United States fleet to electric. We can actually use table salt, sodium chloride, to basically extract the lithium from the ore. And we actually we actually got rights to a lithium clay deposit in Nevada.
Over 10,000 acres.
Over 10,000 acres.
Simply mix clay with salt, put it in water, salt comes out with the lithium, done. And eventually, as we said at the beginning, when we get to this steady state 20 terawatt hours per year of production, we will transfer the entire non-renewable fleet of both power plants, home heating and battery and industry heating and vehicles to electric. And at that point, we have an awesome resource in those batteries to recycle to make new batteries. So we don't need to do any more mining at that point. And you can see why. Yeah. The difference in the value of the material coming back from the vehicle versus the ground, you'd always go to the vehicle. And we recycle 100% of our vehicle batteries today. And actually, we are starting our pilot full-scale recycling production at Gigafactory Reno next quarter to continue to develop this process as our recycling returns grow. Yeah. So we just talked about scaling cathode and recycling. All of the benefits that you just saw are added to this benefit of a 12% reduction in dollars per kilowatt hour at the battery pack level. Almost at our halve the cost goal, but there's one more section. Take it away, Elon.
It starts with having a single piece casting, or a single piece casting for the front body and the rear body. In order to do this, we commissioned the largest casting machine that has ever been made. And it's currently working just over the road at our Fremont plant. That then interfaces to what we call the structural battery, where the battery for the first time will have dual use. The battery will both have the use as an energy device and as structure. It also allows us to pack the cells more densely because we do not have intermediate structure in the battery pack. So instead of having these supports and stabilizers and stringers and structural elements in the battery, we now have a lot more space in the battery because the pack itself is structural. So the volumetric efficiency of the structural pack is much better than a non-structural pack. And we actually bring the cells closer to the center. Because they're closer to the center, it reduces the probability of a side impact potentially contacting the cells, because it has to go, any kind of side impact has to go further in order to reach the cells. You reduce the polar moment of inertia, and that means the car maneuvers better. It just feels better. You don't want to know why, but it just feels more agile. 10% mass reduction in the body of the car, 14% range increase, 370 fewer parts.
In addition to the improvements we just said on enabling additional range and improving the structural performance of the vehicle, it is worth another 7% dollar per kilowatt hour reduction at the battery pack level, bringing our total reductions now to 56% dollars per kilowatt hour.
Yeah.
Range increase, we're unlocking up to 54% increase in range for our vehicles and energy density for our energy products. 56% reduction in dollars per kilowatt hour at the battery pack level, and a 69% reduction in investment per gigawatt hour, which is the true enabler when we talk back about how do we achieve this scale problem here.
Yeah. What this enables us to do is achieve a new trajectory in the reduction of cell cost. I mean, long term, we want to try to replace about at least 1% of the total vehicle fleet on Earth, which is about 2 billion vehicles. So long term, we want to try to make about 20 million vehicles a year. We're confident that long term we can design and manufacture a compelling $25,000 electric vehicle. So